Hi everyone, my name is Josh Adkins, and today I'm going to be talking to you about Monoxalyze, our system to verify smoking cessation with a keychain-sized carbon monoxide breathalyzer. It might surprise you to know that in the United States, 40 million people still smoke cigarettes. That's 17% of the population. Smoking can still be linked to 1 in 5 deaths, and government-related healthcare spending on smoking exceeds our government spending on the environment, education, housing, and science. Now, it's not that people want to or don't want to quit smoking. They do. 50% of smokers try to quit every year, but only 4 to 6% succeed. And that makes sense. It's really hard to quit smoking. It's a very addictive habit. There is, however, one way that we can help people quit smoking. Specific intervention programs can over triple cessation rates. These intervention programs might be something like sending a text message to something when they're about to smoke or when they've just smoked a cigarette, or even paying people to quit smoking. But the first thing people ask when you tell them that you're going to pay people to quit smoking is, how do you know they've actually quit? What's your compliance mechanism to make sure that they don't lie to the system? Well, you might imagine a compliance mechanism that looks something like this. You give someone a breathalyzer, and that breathalyzer reading is then transmitted to the cloud, where the intervention provider can look at that reading. Of course, that leads to the question, is this actually feasible? And the answer is, it is feasible. So it turns out when you smoke cigarettes, carbon monoxide, it goes into your lungs and then gets absorbed into your bloodstream as carboxyl hemoglobin. And then over the next 5 to 8 hours, it's exhaled back out in your breath. So you can see in the plot on the right that after someone smokes a cigarette at the starting line, their carbon monoxide concentration, their exhaled breath, drops off over time. And it's generally accepted by the medical community that a carbon monoxide reading over about 6 ppm indicates that you were smoking. And there are current carbon monoxide breathalyzers on the market. They're made by a company called Monoxalyze, primarily, and they're pictured here. However, they don't really meet all our needs. And the biggest reason they don't meet our needs is that they don't have a verification mechanism. So imagine what it looks like if we want to use these to verify someone has quit smoking. We give a breathalyzer to them, and they take it home and they blow into it, but they can still lie about the reading it produces. So instead, they have to go into a smoking cessation clinic every single week or so, and even that's not providing perfect guarantees that they've actually stopped smoking. Instead, we'd like something that's more mobile and can do the verification in a mobile way. These devices also just aren't very usable. Only 2 of them report data at all, or only two of them don't report data at all, and one of them reports data to a phone through an audio jack. And they're quite large. They're not something that you'd want to carry around every day and blow into every 5 to 8 hours. To solve these problems, we present Monoxalyze. Monoxalyze is a smaller carbon monoxide breathalyzer, which you can see here, and it's quite a bit smaller than the smallest Smokealyzer product, and it's meant to be keychain-sized, so it could go on your keychain and you carry it around. With Monoxalyze, we would give the breathalyzer to a person. The breathalyzer would connect to the person's smartphone over Bluetooth, which could then report the readings to the cloud. So with this system, we solve problems of wireless data reporting, and we've made the device small and more mobile. However, this system, as pictured, still does not provide a verification mechanism, and we've now added the problem that it's an energy-constrained device running on a small battery. So let's see how we can solve some of these problems. So first, let's talk about what we mean by smoking cessation verification. What is the threat model? So you could imagine a threat model of trying to spoof Bluetooth messages from the sensor to the phone, or trying to spoof readings going to the cloud and essentially tamper with the technical aspects of the system. However, we'd like to say 2 reasons why we don't consider this threat model to be our concentration in this paper. First of all, we think existing techniques can mostly protect against this, encryption on our data and so forth. And we also don't think it's the techniques that most people would try to employ to attack the system. We're trying to target average users here, not the computer scientists in the room. So the threat model we really want to outline is non-technical attacks. Attacks like not exhaling during a test, having a friend blow into the device who's a not smoker, or trying to spoof the system with a second device. So let's go through these attacks. How could we prevent each one of them? Starting with not exhaling into the device. So if we give the device to a person and they either don't exhale into the device, making it sense the outside air, or they just don't blow hard enough into the device, emptying their lungs through it, they could make the system think they weren't smoking. To mitigate this, we add a pressure sensor internally. And this is actually a little bit stronger guarantee than you might think, because it's not just sensing airflow through the device, it's actually sensing the humidity in someone's breath. And to show this, you can see the top graph, which measures a dry exhalation, where we simulated exhalation with just air movement that wasn't coming out of someone's mouth, and the bottom graph, which shows a real person exhaling into the device. You can see the noticeable increase in pressure with someone actually exhaling into the device, and the algorithm for verifying exhalation is therefore simply looking and making sure that the pressure continues to increase over time. And we can note the stopping of someone exhaling when the pressure starts to drop off. Okay, so the next attack on the system, giving the device to your friend. Our first defense against this is working with the smartphone as a compliance mechanism. We start by saying we're going to use facial recognition from the smartphone to guarantee that the right person is blowing into the device. So the idea is someone would hold their phone up and start blowing into the device, and as they blow into the device, it would provide facial recognition. This, however, doesn't solve all the problems. Imagine, for example, that you have your phone up and you're pointing it at your face, and your friend next to you, who is a non-smoker, is still blowing into the device. And that's the device that's actually connected to the phone and is receiving readings from. We need a way to tie the device that is connected to the phone over Bluetooth to the user who's blowing into the device. Put another way, we need to make sure the device we're connected to is actually in our frame while we're doing facial recognition. And to do this, we use visible light communication. So I'll go into the details in a second, but the idea is that if the phone is connected to a device it's not looking at, the VLC check would fail, and then if the phone is connected to the device it is looking at, it would succeed. And we do this using a visible light challenge response protocol, where the phone over Bluetooth sends a challenge to the device, which then blinks back that challenge using front-facing LEDs. And this is the response. And through this, we can guarantee that the phone is actually looking at the device which it's connected to. A device would fail the challenge response otherwise. So with those systems in place, we can now step through the verification of Monoxalyze step by step. It would start with someone signing up for an intervention program and registering with it, and providing training data so that the facial recognition knows what to look at. So this would still be a human-in-the-loop procedure, verifying that they provide the right data for facial recognition. When they want to use the device and take a breath test, they would open the app and then take out the device and start exhaling into it, which would wake it up and make it connect to the phone over Bluetooth. The phone would then start doing its verifications. It would do the VLC check to make sure the device is in the frame. It would start performing facial recognition on the user, and it would make sure that the user is actually exhaling through the device. At the same time, the device is going to be collecting carbon monoxide readings and sending them to the phone, and the phone can then send those carbon monoxide readings along with some indication that the verifications have passed to the cloud, where the intervention provider can look at it. And we'd like to note here that all of these steps are really happening in parallel at the same time, and that this testing can be done, you might be able to make it random to make it harder for someone to plan to attack the system. So require a test randomly within some time period. So with that system, what we've introduced is the idea of transitive trust. So we wanted to establish a ring of trust between the device and the user through facial recognition, between the phone and the user through facial recognition, the device and the user through pressure sensing, and the phone and the device through the visible light challenge response. With that in place, we have at least put some effort into solving the mobile cessation verification problem, and we think that it actually will work pretty well. Of course, we're not going to be able to stop every single attack. You will find a way to attack the system, but we want to make it harder. We want to make it harder to attack the system than it would be worth it for a user's time. We still have the energy constraint problem though, so let's look at what we can do to mitigate those problems. We really break the energy problem down into two optimizations. The first optimization is on the VLC challenge response. So you can imagine that blinking the lights on the front of the device could be take a lot of energy, and it does. So we really want to have a fast data transmission rate so that we don't have to keep the lights on for very long. And what we do is we send on-off keyed 3-bit frames, and we actually reduce the energy by making the clock signal embedded by verifying that each 3-bit frame is different. So that stops us from sending arbitrary data, but we can still send random data, and that works for the VLC challenge response protocol. The next optimization we make is to the BLE on the phone. So we first try to answer the question, how many times should a device advertise? And so in BLE, what you do is you send advertisements until the phone, connects to the device. However, you don't really know how many advertisements you need to send, and not all phones are created equal. So you can see the iPhone, for instance, connects to the device in under 5 advertisements every single time, which is a best case energy scenario. The Android phones, on the other hand, are much more variable. And we see the Motorola Moto X particularly takes a long time to connect. So what we did is we took the upper bound on the Motorola Moto X test and said, we have to advertise at least 200 times to verify connection before going back to sleep and considering it a failure. We also see during our testing is that most phones don't accept high connection intervals. And what I mean by this is that after a BLE device connects, it establishes a connection interval, which it will transmit data on. And ideally, we would make that match the data rate if we wanted to conserve energy. However, most phones just don't allow you to do that. And if we really want to conserve energy, we'd like to see more support from especially the Android side of the world on implementing some of these BLE features that save energy. With those optimizations, we look at the battery lifetime of Monoxalyze. So Monoxalyze has a small battery. It has 532 joules of energy. And a breathalyzer test takes about 400.5 millijoule. You see that most of that energy is actually coming from that unoptimized BLE connection I just talked about. And on this energy, we can do over 1,000 breath tests. Of course, when we consider sleeping the device, it lasts 110 days in sleep mode, giving a combined battery lifetime of 83 to 95 days if we assume a few breath tests a day. Now let's look at validation. So in validating the system, we broke it down into the verification parts that I mentioned earlier in the talk. Looking at exhalation verification, we had 10 tests with different people where they would wait 10 minutes between each exhalation, and it would detect the exhalation well every time. We would also try blowing a minimal amount of air into the device, and it would identify that had insufficient volume, and it can easily identify ending the exhalation early so you don't exhale all of your lungs through the device. And the only thing is it doesn't have good detection rates if you do back-to-back testing, because it's using the humidity in someone's breath that saturates in the device, and it won't detect the second exhalation. We note that this isn't the normal case, and also that the failure is an inconvenience to the user, not a security failure. The next thing we do is analyze the VLC processing. So you can see this is what a VLC response looks like from the front of Monoxalyze on the LEDs. It's going 28 bits per second in this video, and that's about the maximum data rate we can get using the phone's frame rate. And what we did is we tested random 12-bit challenges. We did 30 of them and saw that 29 of them succeeded, and only 1 bit was off, giving us a 0.1 bit error rate at these short 5 to 8 inch distances, which is normal for our use case. It doesn't work if you hold your phone really far away from you, so way out here, and it also doesn't work if you have the sun behind you, for instance. But again, we note these are inconvenience, not security failures. The last thing we want to analyze is, can Monoxalyze actually see if people are smoking or not? To do this, we designed two systems, one with each different kind of sensor on the screen. And when we first started testing the systems, we realized that they cross-react to water vapor, which of course isn't good in a breathalyzer scenario. We added some filters to try to filter out this water vapor. However, the cheaper sensor still didn't work, unfortunately, and part of our future work is trying to get that cheaper sensor working better. After we got the system working with the filters, we sent it off to a smoking cessation clinic so that we could do a user study. And the user study had 12 participants where the users blew into Monoxalyze and then blew into the Smokealyzer device, which is now considered the gold standard for the smoking cessation clinics. And you can see that Monoxalyze does pretty well at tracking the Smokealyzer's output. When we look at its actual classification accuracy on the right-hand side, you can see that at 6 ppm, the 6 ppm threshold, it classifies 11 of the 12 people correctly, which isn't a great percentage, but it's actually on par with the current classification rates of the Smokealyzer sensors, just a little bit worse. So we think with more development, we could definitely get there. Last, you're probably wondering, so you've presented the smoking cessation system. It can hopefully stop people from cheating, and it acts as a smoking cessation compliance system, but what other applications could actually use this system? So there are obviously other breathalyzer applications, court-mandated alcohol abstinence, for example, but we're starting to see a lot of companies try to put third-party monitoring in to monitor people in other ways, such as health insurance, seeing what data is coming from people's Fitbits. You might use a Monoxalyze-like system exploiting transitive trust to verify they didn't put it on their dog, have their dog run around. Or you might have other medical devices where you're trying to verify that a device is tied to a person, and then the data that device is reporting to the phone is also being reported correctly, and really giving the doctors more assurance that the data coming from these devices has some reliability. More generally, though, we might be able to exploit properties like transitive trust and these loops using different sensors to improve data reliability and data provenance in general. As we start collecting more data from the physical world, we're going to start wanting more reliability from it and more verification that it is actually the data that it says. So I think Monoxalyze is really kind of pushing this boundary and trying to look at what that looks like, especially in a case with human users. Thank you. Does anyone have any questions?
Okay, any questions about the speaker?
David Coates from Dartmouth. Very nice work. Thanks. Very interesting. I wonder if you could compare it to a similar device that was developed about 5 years ago by Ashu Sabharwal at Rice called the Mobile Spiro. It was a spirometer, a little bit bigger than this. It was meant to connect to your Android phone, and you blow into it to test lung function for people with asthma and such. And it had a camera facing the user for the same kind of purpose of verifying that the right person is using it on board, though.
Okay.
And so I'm just curious if you have compared with that, what the differences might be, et cetera.
So I actually haven't compared to that system directly. I think that, so from what you said, though, it had a camera on board. So obviously one difference would be trying to leverage technology we already have, although that's not an extremely deep difference. You could imagine putting a camera on board our device to really the visible light communication enables it to work with a mobile phone, though. It would be nice to look into the link more.
Yeah, you might, because they have, their goal is measuring pressure, so they have that part already there. And they have, I think, in some of their versions, added sensors. For example, I know of a nicotine-specific sensor that is used in some products now that senses the air and looks for airborne nicotine, which could be also useful in this application.
It could be, yeah.
Sure, I'll send you a link.
Thank you.
Hi, I'm Basima from UNC Chapel Hill. So I was wondering if you could say that why are you using facial recognition to identify a person instead of any other means?
So we have thought about other means a little bit. Facial recognition was nice because it was accessible on the phone. There's a nice body of work that says it can be done pretty reliably, and even more work going into the future where a lot of companies are trying to use it to verify things like credit card transactions and actually looking at 3D facial structure to try to make it even more secure. So that was kind of the motivation behind facial recognition. It was accessibility.
So what will the problem the other means like biometric recognitions or other will have in this scenario?
So you could imagine some biometric markers like using a fingerprint sensor, for example. However, that's not really tying the user's identity in the same way. You could still imagine someone just holding their finger on the device. What facial recognition gives is that it puts the breathalyzer in the frame, so that really helps a lot. You might be able to, So there are obviously other biometric markers, but I think you'd have to stick to things maybe in the face or the mouth area, and like maybe you could do iris scanning or something along those lines would fit well, but we'd have to explore those other options.
Thank you.
Thank you.
Just a quick clarification question, I guess. John Ko from Madrid University. So I might have got it wrong, but I get the impression that the separate components were tested separately. The units were tested separately because So I guess the part that confuses me is that you claim that you let us know that it takes a while for the Bluetooth connection to actually get together. And you say that the VLC is going to be used to authenticate that the device is being used. And I was wondering if that can actually happen simultaneously given the delay and the blowing time.
So it should be able to. If we go back to that plot, it's not the time that's really the concern, it's the amount of packets. So you can see even though these are 200 packets, they're 200 packets at 20 milliseconds. So even that isn't too much delay over the length of a 30-second exhalation or a 15 to 30-second exhalation.
Thank you.
Hi, Laman Ahmed, Intel Labs. Very good work. I was just wondering, have you looked at whether there's anything about somebody's breath that could be used as a biometric?
We have thought about this. We see variation from user to user even in doing the actual breath tests. So certain users have more humidity in their breath, we think, and it causes different kinds of error in the carbon monoxide signals we get out, and also the pressure readings are slightly different. That might not be quite unique enough to actually identify users, but I'm sure there could be more unique properties.
Maurizio Bocca, Bosch Research. So basically, I could take a photo of a friend of mine and just put it in front of the phone, and that would be it.
This is something we thought about. There's actually facial recognition systems that try to look at the 3D structure of the face now, and our system doesn't integrate that because it's a high technical challenge and it's not really our field, but you could imagine in the future that facial recognition is probably good enough to stop those attacks. You could also imagine a facial recognition system where you're maybe requiring a sweep around the face, trying to get some more 3D structure of the face and stop against that 2D mask attack that you described.
Okay, any other question? So if there is no more question, let's thank the speaker again.